The existence of the mass gap is dictated by what is happening inside a massive star as it nears the end of its life. Young stars burn hydrogen in their cores via their intrinsic nuclear fusion processes. In massive stars, the dominant version of this process is known as the carbon-nitrogen-oxygen (CNO) cycle. This refers to a long chain of reactions involving hydrogen, plus those elements, that eventually produce helium and release a lot of energy to power the star. However, once the star's core runs out of hydrogen, its energy production falters. Without enough energy to hold the star up, the core begins to contract under gravity. This increases the core's temperature by millions of degrees Celsius, until it's hot and dense enough to begin burning helium and temporarily halt the contraction. At this stage, the star is like an onion, with various layers. Its core is burning helium. Around the core is a non-burning layer of helium, and ordinarily, around it is a shell that's still burning some leftover hydrogen to produce even more helium that sinks to the stellar core. This extra helium further increases the core's mass and temperature, speeding up the nuclear reactions which control the star's evolution. Ultimately, this leads to a supernova and usually either a neutron star or a lone black hole, depending upon the compactness of the star's core. In the case of stars with 130 to 250 solar masses and fairly primitive chemical compositions, they can sometimes explode and utterly destroy themselves in a so-called pair instability supernova, leaving nothing behind. By contrast, black hole mergers are the product of massive binary star systems. During the time that they still exist as stars, the close companions are able to steal matter from each other, stripping away each other's hydrogen-burning shell. Without this shell, a star's core doesn't gain that extra helium, which changes the star's evolutionary trajectory. Conditions inside the core of a star that has lost its hydrogen shell are such that thermal neutrinos, tiny, ghost-like particles that spontaneously form, escape the star, carrying some of the core's thermal energy with them. This lowers the temperature of the core and slows down nuclear reactions. The result is a decrease in energy production which allows the core to gravitationally contract some more. This leads to a very dense core that, when the star exhausts all its nuclear fuel and dies, can collapse to form a black hole. In a binary system, this can lead to two black holes that eventually merge with a chirp of gravitational waves. Because of a complex interplay between neutrino losses, nuclear burning, and core contraction, we find that stars of specific core masses are more prone to collapsing to black holes rather than exploding as a supernova and leaving behind a neutron star, said Schneider. This interplay leads to common black hole masses, according to the calculations of Schneider, Laplace, and Podsiadlowski. In their models, the black hole masses tend to converge on two values, which are 9 and 16 times the mass of our Sun. These values are very close to the peaks that have been observed in the gravitational wave data, which are at about 8 and 14 solar masses, so they don't exactly match, but remain within observational uncertainties.